manufacturing of text principles we went. So what you mean by manufacturing text principle is that in all the VLSI subsystem whatever we have designed, so it is necessary for us to incorporate the testing circuits. It is necessary for us to incorporate the testing circuit. Why? Because it proceeds us to have a concurrently with the architectures what we are going to consider. It enables us to have a concurrency in the architecture whatever we have considered, and the main purpose of this manufacturing testing is to screen out most of the defective parts before they are shipped to the customer. So as I discussed in the earlier classes or in the last class, so the manufacturing test, whatever we are going to do it in order to screen out or in order to segregate the defective parts which are there before we deliver the end product to the customer. So how we are going to do that? We are going to do that through the use of the analysis of the fault models. So we have some fault models are there, some predefined fault models are there depending upon the applications what we have generated. So based upon the applications what we have generated, so we will be using the different kinds of fault models. So basically what you mean by this fault model is, so they will analyze the various functionalities within the block, and if there is any fault is generated means that will be highlighted through the use of these fault models. Okay, so since it enables us to provide a faults within the circuits what we have implemented, so therefore we call it as a fault model. Therefore we call them as a text patterns as a fault models. Okay, so there are different types of fault models we have. So the first one we call it as a stuck at model. We call it as a first model as a stuck at model we call it as, and one more model we have the short circuit or open model, open circuit model we have. Okay, and those things yesterday we have discussed. So the first one we call it as a stuck at faults, the stuck at 0 or a stuck at 1 model we have. So in the stuck at model, basically what we are going to do is a faulty gate input is modeled as a stuck at 0. If the gate whatever we have used in the implementation of a basic element, if it is fault has been generated in the gate level means or in the gate terminal means, and that we call it as a stuck at 0 model or stuck at 0 model we call it as. Okay, so depending upon the fault what it has been generated in the gate level, either it may be stuck at 0 or it may be stuck at 1. Okay, so what it does, it describes. Okay, stuck at 0 I understood and stuck at 1 I understood. So what it describes, it describes the board level design. So what is the board level we have designed, and it will design us, it will enable us to determine the adequate number of modeling faults. It will enable us to identify the adequate number of modeling faults. Okay, so there are two types of stuck at fault models we will be getting. The first one we call it as a stuck at 1 model, and the second one we call it as a stuck at 1 model. So depending upon the logical values, the gate which is not able to transmit from input terminal to the output terminal, so based upon that we may get a stuck at 1 means the output will be stuck to 1 only, it will not change for the particular input combinations. The output has to change from 1 to 0, but if your gate is not triggered properly means then the output will be remain high even though the subsequent input changes. So that mechanism we call it as a stuck at 1 model. Similarly, stuck at 0 is for the certain input signaling methods whatever we are going to pass for the VLSI subsystem, the output has to shift or the transition shift switch, the output has to switch from 0 to 1 or 1 to 0. In the case of stuck at 0 model, so it will be the output will be stick on to the 0 level only, even though the subsequent inputs will changes, so that the output has to shift from 0 to 1 because of the infunctionality or because of the defects in the gate level manufacturing process. The output may not switch from 0 to 1, and that we call it as a stuck at model or a stuck at 0 model we are going to call it. And one more type of the fault model what we have going to generate or what we are going to use in the VLSI subsystem is the short circuit and the open circuit faults. The short circuit or open circuit faults. Okay, so you can see in the diagram the shortened faults bridge faults also. We call it as a shortened faults, as a two bridge faults also we call it as. So which has been depicted in the bridge diagram. You can see here the shortage of the two terminal, that is, it may be gate to gate, it may be drain to drain for the PMOS, or it may be the same thing for the NMOS also. It may be drain to drain connection, or it may be source to source connection. So such a mechanism we call it as a shortened, or it is also called as a two bridge faults, as you can see in the diagram. So here in the S1, the short S1 will result in stacked 0 fault at the input. So you can see here for the S1, we are talking about the S1, the shorted fault. The short S1 will result in a stacked 0 fault at the input terminal. Similarly, the short S2, which will modify the functionality of the gate terminal. Similarly, the short S2, whatever we have done, right? So if there is a short circuit is happening between the that is the drain of the PMOS to the source of the NMOS, means then that short we call it as a shortened stacked 1 method. And because of this stacked 1 method, the functionalities of the gate will changes, and it also ensures that the accurate modeling of the fault at the transistor level. It also ensures us to have a accurate modeling of the faults at the transistor level. So for example, if we consider a simple NAND gate, the intermediate node between the series of NMOS transistor is hidden by the schematic diagram. Okay, so what do you mean by this? So it is nothing but when we use the implementation of the NAND gate by using CMOS technology, the intermediate nodes which we are going to use in between the series of NMOS transistors, it will be hidden from the schematic diagram, and that we call it as a short circuit fault. And in the case of NOR gate, we need to have an addition of the two or more ORing, and it has to be take a complement of that. In such a cases, we will be getting a open circuit fault. And one important particular problem that will be arises when we go for the VLSI, that is CMOS technology implementation, is that it is possible for us to have a fault to the combination circuits also and for the sequential circuit also. Okay, so means what? In the CMOS VLSI technology, it is not only we will be getting the faults for the combinational circuits also, we will be getting the faults for the sequential circuits also, and by using this open circuit and short circuits, we can able to convert the combinational faults into sequential faults through the use of this short circuit or a open circuit faults. We can able to do it. Okay, so this is related to the open circuit and a short circuit fault. So you can see in the diagram, of course it is a combination circuit fault, that is nothing but it is a NAND gate, NOR gate implementations whatever we have used, and this NOR gate implementation we can able to convert them into a sequential circuit with the use of this bottom line diagram. Okay, so that is the beauty of your open circuit or a short circuit fault model. Okay, so these are the things what we have discussed in the yesterday's class. So this is the defect, how we can able to create a static IDD current because of the short VDD between the connecting wires of the powering signals to your main circuit. So there also there will be a defect will be introduced in the static current which is flowing across the transistor element. So that has to be also taken care during the open circuit or a short circuit fault model detection. Okay, and after that it is necessary for us to know, so what are the things we need to understand, when we go for the analysis of these faults. It may be through the use of stacked 0, or it may be through the use of stacked 1, or it may be use of a open circuit or a closed circuit. It is necessary for us to understand some of the parameters which we go for the analysis of the fault model. So what are the analysis we need to do is based upon the observability. Based upon the observability, we need to see how best the fault is working. Based upon the controllability, based upon the control ability, we need to judge whether the fault model we have taken, whether it is applicable for our VLSI subsystem or not. We need to check it out. The next one is based upon the fault coverage. So up to which extent I can able to identify the faults in my design based upon the type of the fault model what I have chosen. So that will corresponding to the fault coverage. So that has to be studied. The next one is automatic test pattern generation. So this is a very important methodology which we are going to use in IC industries in order to find out the faults with the use of fewer input sequences, that is special input sequences. So for these pure special input sequences, for all the circuits it is possible for us to generate the faults, or it is possible for us to identify the faults. So those mechanisms we are going to call it as an automatic test pattern generation. And there is one more method what we are going to do is, or we are going to call it as delay fault testing. So in the delay fault testing, what happens is, so because of the parasitic generation of the metal wire interconnects, there will be failure will occurs in the VLSI CMOS system that will reduce the performance of the functionality of some of the subsystem, and it will also affect the timing constraints of the device. So such a mechanism or such a timing representation or such a timing analysis, we call it as a delay fault testing. So the first one is, it is necessary for us to understand what you mean by observability. So the observability, it is a measure of various metrics of the design to predict the output of the integrated circuit. So what do you mean by observability? It is the measure of various metrics of the design to predict the output of the integrated circuit. So we need to have some measurements, or we need to have some metrics. So if I measure those metrics, means then I can able to predict what will be the output of the integrated circuit. So that corresponding to the observability. So whatever the metrics we are going to consider, it should be relevant when we want to measure the output of the gate within the larger circuit to check the functionality. Means whatever the matrices we are going to check, it's not that it is only working for one or two parameters. So the matrix what we are going to consider, it has to measure the outputs for the gate within a larger circuit to check its functionalities. For all the functionalities whatever we have designed, so for all the functionalities, if that matrix is responsible, means then that we call it as a miniature or an important matrix which has to be evolved for the identification of the faults in the VLSI subsystem. We need to understand. The second one we call it as a controllability. So what do you mean by controllability? It is an internal circuit node within a chip in order to measure the ease of setting the node 1 or a 0 state. What do you mean by controllability? It is an internal circuit node within a chip which is measured with which age we can able to set the node either 1 or 0. Okay, and this matrix, it is important when we are assessing the degree of difficulty of testing a particular signal within a circuit. Okay, you try to understand what you mean by this is, it is the measure of internal circuit node within the chip with which age you are going to set the node either 0 or 1. By using this, it will assess us to find how difficulty for the testing of a particular signal within the circuit. Okay, an easy controllable node would be directly settable via the input paths. Okay, so this is about your controllability. And the next one we call it as a fault coverage. So what do you mean by fault coverage? So we are going to calculate the fault coverage by using the following mechanism. Okay, so what is the mechanism? Each circuit node is taken in a sequence and it is held at stuck at 0. So how we do this fault coverage is, the each circuit node or each circuit element will be taken in a sequence and it will be held at a stuck at 0. And then what we do is the circuit is simulated with a test vectors comparing with the chip output with a known functional machines. So we are going to use a finite state machine which is a known for the designer. With the use of the known functional finite state machine, we are going to simulate the circuits by using a different test vectors based upon the finite state machine. Next, if the circuit with no node artificially set to 0, if the circuit, it is not artificially set to 0, or if there is any discrepancy in detected between the fault machine and the functional machine means, then the fault is marked as detected and the simulation is stopped. Okay, so how you identify this fault coverage is a circuit with no node artificially set to 0. So means manually we are not going to set to 0 or 1. If there is any discrepancy is detected between the fault machine, that is a finite machine what we have used, and the functional machine, and a fault will be marked as a detected and the simulation will be stopped. Okay, and this process will be repeated for setting the node either to stuck at 1 or stuck at 0. In turn, every node in stuck at 1 or a stuck at 0 will be sequentially false off. Okay, the fault coverage of a set of test vectors is the percentage of total nodes that can be detected as a faulty when the vectors is applied. So we will be having our test pattern vectors. When we apply that test factor vectors, the percentage of nodes which has been defected through the use of those test pattern, we call it as the percentage or the fault coverage range. So for the good designer, the fault coverage range has to be minimum. The next one we call it as a automatic test pattern generation. So what do you mean by automatic test pattern generation is, so in the IC industry and the circuit designing phase, the designer will implement the functions, that is the functions of the Boolean expressions in the RTL or a schematic level. Okay, and what they will do is they will mask the layout and they will test it for the different test cases. So for the different cases, the designer will test it whether it is working fine or not. Okay, and in many ways what the test engineers they will do is they will use the Sherlock Holmes of industry and the reverse engineering circuit and the diverging test that they would test the circuit in an adequate manner. So in most of the cases, the test engineers they will use the Sherlock Holmes of industry, that is one of the method what we are going to use it, and we are going to use a reverse engineering mechanism in order to identify the faults within the circuit. Okay, and for the longer instant of time, what we are going to do is we will implore the circuit designer to include extra circuitry to ease the burden of test generation. So we will be having an additional generation circuit. So with the use of this additional generation circuit, it is possible for us to generate a test patterns, which is possible for us to generate a test patterns. Okay, and in addition to that, whatever the tools we are going to use for the improvement, they should not have a burden of generating the test as we were used to do it in a ATPG methods. So means what? Whatever the test pattern we are going to use in order to generate the faults within the device or within the application, they should not generate additional faults as it was done in the automatic test pattern generation methods. Okay, so this is about your automatic test pattern generation. Okay, So this is the delay fault testing what I told you in the earlier classes. Delay fault testing, it is nothing but we need to find out the delay faults which will occur in the parasitic generation of the metal wires which are interconnects. Okay, and failure will occur in CMOS technology that used to the functionality of the circuit untouched. Okay, but it affects the timing constraints. So if it is affecting the timing constraints, mean such a faults we are going to call it as a delay faults. Okay, so we will stop it over here only. The remaining thing, that is design for testability. There are three main approaches are there for the design for testability. So one we call it as a ad hoc testing, scan based approaches we call it, and one more we call it as a built-in self test is there. So all those details we will see it in the next class.